In lesson 8.5, we were introduced to the idea of logarithms being the inverses of exponentials, and we looked at the logarithmic functions. Now we're going to take a look at some properties of logarithms. Before we do that, we are going to review properties of exponentials because they are very much related. So we remembered if we have the same base and multiply powers with the same base, we can add the exponents. If we divide powers with the same base, we can subtract the exponents. If we have a power raised to a power, so 10 to the x raised to the y power, it's just 10 to the xy. These were a couple properties we learned. Log base b of b just equals 1, which makes sense if we change it back into exponential form. And then log base b of b to the 20th just equals 20, just equals this exponent up here. So one property of logarithms, the property of equality. For a positive b that doesn't equal 1, so your base is positive and can't equal 1, and a positive x, which we'll hone on that later, this has to be a positive also. Later on we'll solve equations, and if you're trying to take the logarithm of a negative, that doesn't work. So if you ever get a value here that's a negative, you can't do that. So anyway, that was a little side note. But log base b of x is equal to log base b of y if and only if x is equal to y. So these parts here have to be equal to each other. Here are some properties of logarithms that come really from these properties here. You'll see some similarities here with the multiplying powers having to do with adding exponents. So here's our exponent properties, and then here's the logarithm properties. And it will take a little time to get used to these, but you'll be able to use these and apply these. So log base b of two things multiplied together, m times n, you can actually split that up and say it's log base b of the first one plus log base b of the second one. So multiplication of logarithms ends up having to do with addition, just like multiplication of exponentials or powers had to do with adding the exponents. Log base b of m divided by n is log base b of m minus log base b of n. And then the last one, log base b of m to the p. This p we can actually think of it as coming out front. So that's equal to p log base b of m. That has to do with a power raised to the power you multiply. So we have m raised to a power we actually can multiply by that p. So those are the properties. You might want to have a copy of them close by as we look through a couple of examples, but I will try to explain them as we work through. So this says write each expression as a single logarithm. A single logarithm. So right now it's a logarithm minus another logarithm. So it's two logarithms, two terms. Well, we can use our properties. We know that if we have log base b of m minus log base b of n, and actually I'll go back and show you or mention something that it's in this one. We're actually going to start with this. Sorry, actually in this one it's this, and we're going to change it to one term. So we're going to take two terms and change it to one term. So obviously it's an equality, so these properties work both ways. You can split up things that are multiplied into two logarithms, or two logarithms that are added that have the same base can be combined by multiplication, or in this case division. So let's go back to our example. When we subtract, this is just going to be log base b of m over n. And so in this case we have log base 2 of 32 minus log base 2 of 8. They have the same base, so we can say this is going to be log base 2 of 32 over 8, which obviously 32 divided by 8 is 4. Log base 2 of 4. So it said write each expression as a single logarithm. There it is, a single logarithm. Next one, we're going to use a couple of our rules here. We had that power rule, which was last, and so this 3, let me go back to it. Normally we had the p here, or I started by showing you had the p here and it could be moved out in front. Well, now it's out in front, we can actually move it up to be an exponent. So we can write this 3, that's going to move up here and be an exponent of this. And so I'm going to do this in 2 steps just so you can see both steps individually. Log base b of x cubed plus log base b of y. Well, we have a logarithm plus a logarithm. From our properties, we know we can combine that into one logarithm, log base b, and we can multiply these 2 things, x cubed times y. And that has to do with this property right here. 2 things were added so we can combine them into one logarithm, m times n. So these 2 will write each expression as a single logarithm, which sometimes we'll see we condense it. And then in this one we're going to expand. So we're going to span this into more than one logarithm. So let's start over here so we have some room. I'll just rewrite this, but I'm going to rewrite it instead of having cubed root. We learned we can write that as a rational exponent, so this is d squared over c to the 1/3 power. And we can do this a couple different ways. Let's just start this way. This 1/3 is exponent, so this can actually be moved out front by that power rule. And so we'll have 1/3 times the log base 3 of d squared over c. We just have to be careful here because now we have 1/3 times this whole thing, which now when we split this up because it's division, we're expanding because it's division, we have this 1/3 out front. So we can break up this division into a subtraction of the numerator minus the logarithm of the denominator, so d squared minus log base 3 of c. And even within here we can use this power rule again. This 2 can come out front. Now it comes out in front, right in front of this one. And so we have 2 log base 3 of d minus log base 3 of c. And we could distribute in this 1/3 or not. It doesn't really matter. I did want to show you just a different way of doing this, where we actually use a rule of exponents first. So this is d squared over c to the 1/3. Well, when we studied exponents, we learned that this exponent on the outside can go to each factor in here. And so we could say this is log base 3 of d to the 2/3, because I'm multiplying, over c to the 1/3. Sorry, this is getting messy. My 3's aren't looking right. So that 1/3 can be multiplied by each exponent here, realizing that this is an exponent of 1. And now we can use our logarithm rules. So this is log of a quotient, so we can split this up into log base 3 of the top one, d to the 2/3 minus log base 3 of the denominator, which is c to the 1/3. And we can use this power rule to bring these exponents outside. So we have 2/3 log base 3 of d minus 1/3 log base 3 of c. And these two are the same. Notice if I just distributed in this 1/3, we get the same thing. So either answer here is fine. So that's expanding. Here's just using some more, using the properties of logarithms a little bit more. We have a couple definitions here. We know the log of 5, which really, remember, this is a base 10. It's a common log, equals 0.699, and log of 7 is about equal to 0.845. Find a decimal approximation for each logarithm. So there's going to be a couple under this example. Well, what we need to do, we know we have a 5 and a 7. So what we're going to want to do is we're going to try to figure out, does 175 compare at all or involve 5 and 7 at all? So if we think of 175 over the side here, I'll write this. 175, good old factor tree, is 25 times 7, and 25 is 5 squared. So really, we can write this as log base 10, but not written there, of 5 squared times 7. And that's good because now we have log of 5 and log of 7. So let's go ahead and expand this a little bit. So these are two things multiplied together. So we know when we have things multiplied together within our logarithm, we can split it up. So log of 5 squared plus log of 7. That's using this property here, product property, splitting up, multiplying things into adding two logarithms. And then this 2 can come out front because of the power rule. So we have 2 log of 5 plus log of 7. And now in our directions, these two logarithms are defined. So this is 2 times the log of 5, which was told was 0.699, plus log of 7, which was 0.845. And you can figure out what that sum is. You can multiply 2 times 0.699, add that to 0.845, and you get 2.243. So you can just do that on a calculator or do it off to the side with pencil and paper. So there's one. Moving on to the next one, same directions but a different one here. Here we have log of 2, which log of 2 seems a little bit interesting because we're given log of 5 and log of 7. So we have to figure out how can we get a 2 from that. Well, we have to make sure we understand that this is a base 10. And so base 10, we can use 10s in here also. So I'll write it in here. 2 is actually 10 over 5. But if we remember from before, log of 10, which remember this is an understood 10, log base 10 of 10 is simply equal to 1. And so that's going to help us in a couple minutes or in a minute or so. So now this is a division problem. Maybe didn't recognize that there was this 10 in here, but we have log of 10. So this is a quotient, so we can change that into subtraction of 2 logarithms. And we know the log of 10 is 1, minus the log of 5, which is 0.699. You subtract those, and you get 0.301. So log of 2 is about 0.301 using the fact that log of 5 is 0.699 and log base 10 of 10 or common log of 10 is equal to 1. So still using properties. In this one we want to solve, and I mentioned before when we solve, if we get an x value, so an x can be negative, like if we had a -1 in here, -1 plus 3 is positive 2. We can take the log of a positive, but if this whole thing in here ends up being a negative, we have to discount that solution. So we're going to start here. We have this equation. Remember, if we have log base b of something equal to log base b of something else, those two things are equal to each other. The problem is we have this 2 out front. So what we actually do is we just use the property, the power property, and so we can write this as log base b of x plus 3 squared is equal to log base b of 36. And now we do have a logarithm equal to a logarithm, and so x plus 3 squared has to equal 36. We could solve this a couple different ways, but the easiest way is probably just to take the square root of both sides. So we take the square root of both sides. Here we get x plus 3. Over here, take the square root of 36, you get plus or minus 6. Subtract 3 from both sides, and you get x equals negative 3 plus or minus 6. And we want to get both of these solutions, so we have negative 3 plus 6. Negative 3 plus 6 is 3, and negative 3 minus 6 is negative 9. Now we have to check our solutions because we can't have a negative in here, so let's check 3. We have 2 log base b of 3 plus 3 equals log base b of 36. Well, this is a 6, and if we put the 2 up there, that would be squared, so we would have log base b of 6 squared equals the log base b of 36. And 6 squared does equal 36, so that works. And now let's try negative 9. Got 2 log base b of 3 plus negative 9. Sorry, I should have put that as negative 9 plus 3. So putting in x, negative 9 plus 3 equals log base b of 36. Negative 9 plus 3 is negative 6, and as mentioned before, we can't take the logarithm of a negative, so we have to stop here. This doesn't work. Don't keep going with your properties because you might think, oh, well, if I square the negative 6, it works out. We can't. We have to stop here. You can't take the logarithm of a negative, so negative 9 does not work. So our answer in this case is just x is equal to 3. And so we are able to solve a logarithmic equation. We used one of our rules of exponents, and make sure you go back and check because we can't have a negative logarithm.